All right. Welcome back, everybody, to another fun episode of TechXperts. A little bit about the series. TechXperts is designed to showcase innovative technology in the architectural, engineering, and construction industry. Today, our guest is Robert Strong with CFT. Robert, could you do a little introduction?
Yeah, absolutely. My name is Robert Strong. I'm a licensed professional engineer. My background's in nuclear power. I operate nuclear reactors in the Navy. There's some Navy nukes in the industry. A few of us do different things in this in the tech industry for sure. When I got out of the Navy, I was a NETA testing engineer. A lot of NETA testing going on out there. I was the lead acceptance testing engineer for ETI in Silicon Valley during the dot-com boom, end of the 90s kind of time frame. Moved on from there, was a project manager with Cupertino Electric, Frank Electric branch out there, and did a lot of work. That's how I got my PE license, was designing building jobs and then running the crews. So had to clean up my own mess, basically. Sure, is how that works out, right? So no more just having FPs and field problems. Yeah. They become yours. Then I like to say I moved out of California, grew up in Dubuque, Iowa. So grew up in the Midwest, gotcha. Moved to Colorado and started this rack at CFT, so Critical Facilities Technology. Loosely a manufacturer's rep firm, but we do a lot of things to help engineers and end users, everybody design, build data centers all over the world, frankly. We've done a lot of projects. A little bit about my background. On top of that, I was E&R Magazine Top 20 Under 40 engineer. I wrote a scientific research paper on holistic data center design that was published internationally, spoke on that. And then I was have an international award of data center design and engineering from the Uptime Institute. Okay. So people not familiar with Uptime, they developed the tier standards, right, for data centers, 1, 2, 3, 4, tier level, stuff like that. So, a lot of fun. Building a lot of cool, really complex projects over the years, and just love, helping people out with it. It's a ton of fun. It's great.
Seen it all, done a little bit of everything.
Yeah, it's fun. Our company motto is we're dumb enough to try anything. And, we stay true to that. Okay. So, if it's a challenge and it's out there and we feel like we can knock it out of the park, we're going to give it a shot and then go from there. And so, we have a lot of fun with it.
All right. Cool stuff. So today, I know we're going to focus on UPSs.
Sounds great.
Uninterruptible power systems. Yeah. Do you want to talk a little bit about what it is and kind of some configurations maybe?
Yeah, certainly. First, I'd just like to hit on, why do we want a UPS, right? Why does a customer want a UPS? Ultimately, it's about the load. When we talk about applications for UPS systems and we talk about the complexity or the type or style of UPS, it ultimately comes back to what is the load we're trying to keep up and running, right? And so as time's gone on, and UPSs have become more affordable and more common, we're supporting more things with UPSs than we did in the past, right? Some things we didn't think traditionally we would support with UPS, and now, hey, why not back that up and keep that system running? So it's been more prevalent, and there's more and more equipment out there that we do keep up with UPSs, but ultimately it's really about how important the load is to that customer and that application, and going from there. And then, of course, the type of technology and how it's backed up, right? So it really is load-driven. Right. For all of that stuff. So what's a UPS or uninterruptible, power supply do? What's it going to do? So we want to take the incoming utility source, right, that's then feeding this load that we have, and how do we want to protect it, and what way do we want to protect it? Well, there's a couple of different versions out there. Most of your smaller rack mount systems are going to be line interactive style systems, where ultimately the load is still technically being fed directly by the utility source, but we have essentially a sidecar inverter system with a battery that's going to say, hey, if we see an outage, we're going to preclude that outage by interrupting that or intercepting that outage and ultimately supporting the load through that. But it doesn't really have a lot of filtering capability, so transients or issues that may exist on the utility side are ultimately going to be felt by the load to some degree. And then we have what's more common on the larger systems is your online double conversion, right? Now, the word online kind of comes from historically the term that the inverter is always on, right? So that inverter, because it's part of the circuit, is on and creating a sine wave out to the load, right? Where your line interactive system, your inverter as that sidecar isn't really supporting the load. So it's not online, right? So a different type of online technology, or not online, excuse me. So if we go to a double conversion UPS, we're actually going to convert the energy twice, hence the double conversion term, right? So we're going to take the incoming AC energy, we're going to convert that all to DC, feed a common DC bus in the middle of that. Your energy storage system is going to live on that DC bus, right? So it could be lead acid batteries, wet cells, valve regulated. Now more and more it's a lithium ion. In fact, lithium's really kind of taken over the industry as a whole. It's hard to find larger systems that aren't specified lithium, and even some of the smaller ones is becoming more prevalent. We're kind of seeing the marketplace get definitely squished down from the top with lithium, but also now kind of coming up from the bottom. It's almost the middle layer that doesn't have lithium right now, so it's kind of a little interesting. But ultimately, that DC source, also flywheels, other systems, which flywheels not nearly as prevalent at this point. And there's your DC source, and then your inverter is ultimately going to take that DC source, create its own sine wave, and then feed the load, right? So ultimately that load will be fed by a sine wave that we create in the box with its inverter, right? So a couple other components in there, as I'm kind of drawing it out spatially here in the air, would be the static switch, right? Now your static switch serves a few functions. Ultimately, one thing that's important to know, right, is because the inverter is creating its own sine wave and our utility source it's also another sine wave, they are not going to be in sync with one another, right? So if I go to a mechanical bypass method, I'm going to parallel two sources. It's usually not a good thing, right? Things usually tend to come apart when we do that, so unless you time it just right, don't recommend trying that. Seen that done, it doesn't show up well. But ultimately, because we have two separate sources and they're not going to be in sync, right? They're going to be all over. We can use the static switch ultimately to say, hey, inverter, let's get in sync with the input and make sure that the outputs are the same. So now they're in sync with one another, and now we can go ahead and close that bypass breaker, right? Or switch or whatever device it is. Normally there's an indicating light on the switch that says okay to operate, or you'll see an indicating, or you might have a Kirk key system, right? It might be a Kirk key system that allows you to close that breaker depending on the level of design of the system. But once those are in sync, then that static switch will allow us to go to a mechanical bypass. We can isolate, turn off the UPS, do maintenance. Those are kind of your main components. The other big piece of the static switch that's important is for fault current. So if I'm feeding some type of downstream load, and I have some breakers and distribution here, and I need to clear a fault, right? I need a breaker down here to do a protective action to protect the load that there's been some failure, whatever happened down the line, or some kind of shorter ground. The energy required for that breaker to trip is not going to be able to be provided by the inverter. Some instances it might be if it's really light, but for the most part, the inverter is not going to provide that energy or responded time to give all of that energy. So we need the static switch to allow the energy to pass through the UPS to the load. Right, so that's the other main function of the static switch that's essentially required in the UPS for that function, for that. So another big piece.
Yeah.
So, yeah, very good. A lot of people are confused about, fault current and what happens through UPSs, but ultimately, if there's a downstream fault, the UPS is going to just pass through whatever's available on the input. So ultimately, your fault current on the output is the same as your input. Be prepared that everything's going to come through if there's a downstream fault.
Gotcha. Okay. We talked a little bit, like you mentioned, your energy storage methods. A lot of different battery types, and you brought up flywheel.
Yes.
So does a flywheel UPS still use a battery to some degree?
No, it should be. Once the flywheel's up and running, right, it's going to spin. There's a few different variations out there. We can kind of get into the different types of them. Some are heavier and spin at a lower RPM, and then some of them spin at a very high RPM that are relatively smaller footprint. I mean, those are your two kind of main ones. Your active power is your bigger, heavier one, and your Vicon is your lighter one that spins faster. Active power essentially connects theirs into their own system, which is ultimately a line interactive style UPS, but for a large module system. And then your Vicon's more of your standalone plug and play into other manufacturers' UPSs. Ultimately, you're taking inertia as a form of energy, right? And then we're trying to convert that into energy in some way.
Right.
There's some really cool applications for flywheels. Medical imaging was always probably the best application for flywheels historically, just because medical imaging is really hard on batteries. When an MRI clamps and all those magnets turn on, there's a lot of inrush that comes through the UPS, and sometimes that actually can hit the DC bus, where the batteries will actually see that normal operation as a brief outage, And when that happens, of course, battery life is shortened every time it sees an outage. So flywheels were perfect for that because they could take those little hits and just speed back up, right?
Okay.
So they were great for that application. Outside of that, they tended to struggle. I mean, we've done several flywheel installations, but they're usually so much more expensive. And a lot of customers are afraid of that, 30, 25, 40-second runtime that you get with a flywheel versus the battery.
Yeah. Not
Not that, frankly, anybody's going to fix anything in 5 minutes. They're not going to fix in 30 seconds. But that was always an issue for specifications and the price. When everybody else is specifying something that's got 5 minutes of runtime and you're saying, hey, I'm going to give you 30 seconds of runtime for 30% more cost.
Yeah.
It's difficult to fit that into a relatively commoditized industry. So they've always kind of struggled. I think historically flywheels probably never been more than about 5% of the industry at any given time. They've always kind of just been a little piece. Ultimately, talking about different types of battery storage, lithium seems like it'll probably be the death of just about every other form of storage at this point. Definitely valve-regulated batteries have taken a massive hit, especially on large systems. I'll be surprised without some major changes that I can't foresee in the industry. I'd be shocked if there's valve-regulated lead-acid batteries and UPSs at all in probably 5 years. Is probably the time frame.
Wow.
Maybe it might extend a little bit longer with some different changes in tech, but as the battery manufacturers kind of keep coming out with new tech in the lead acid side, it just doesn't seem to quite be able to catch up with how commoditized the lithium side is, and the price just keeps coming down on lithium and just puts so much pressure on the valve regulated batteries. It's really difficult. And your lithium is about 5 times the energy density for a regular lead acid battery. So when you start to put that together with, we're always constrained for footprint, and we're trying to put, our electrical rooms and our support rooms are getting smaller and smaller and smaller. It's hard to win that footprint battle, even if the cost battle isn't there.
Yeah.
Lithium has just been, it's been pretty incredible. I mean, from my perspective, 200 kW has been kind of the cutoff. I don't know that I've specified or seen a lead acid battery installed on a UPS over 200 kW in at least 5 years.
Wow, really?
It's been that long that the lithium prices have come down and been that competitive. Okay. And above that, lithium's usually less expensive now than lead acid is anyway, which is kind of almost a surprise in its own right.
Yeah.
But lithium-ion batteries, I mean, we're riding the coattails of the automotive industry for the most part, right? As automobile industry, brings that manufacturing cost down so much, and the fact that it's a global industry at this point, we're able to take those form factors that ultimately line up with vehicles and have them modified for applications inside of UPS support rooms and stuff in their own special cabinets. Sure. And it works incredibly well. So it's pretty neat.
Yeah, I mean, I'm seeing a lot of lithium ion, and not necessarily just for UPSs, but their form is so small. I mean, it's a standard 1U deal that fits right into the rack, slides in and out. That's it.
Absolutely, yeah. They're in everything else. They're in our phones. We used to talk about NiCads or nickel metal hydride, and those are really transient technologies, right? And they just always work, and you can tell by how long we spent at them, right? I mean, about the time you had NiCads show up in your drills and power tools and your radio control cars and stuff and things like that, immediately you were all onto nickel metal hydride, and you're like, hey, here's a better battery already. And then about the time nickel metal hydride got into anything, you already started hearing about lithium. Well, we've been on lithium for so much longer than all of those. So there's no doubt that the science and the engineering in the background of lithium says, hey, this is the place we're going to stay for a while, right? We're going to really develop solutions around those types of batteries. Not that there aren't other good alternatives, and hey, we'd love to see more types of batteries and better alternatives, and maybe ones that are more environmentally safe or easier to mine. I mean, sure, we'd all love to make batteries out of wood and whatever, but we don't have that. So it's an interesting thing. It's a cool part of the industry to be a part of and see kind of all those changes and the different types and form factors of energy storage as a whole.
Right. So converting from AC to DC and then back to AC. I know your sine waves get chopped up. They're not exactly the cleanest. Yes. So does UPS help with cleaning up sine waves and filtering out anything else?
Absolutely. Excuse me. First and foremost, right, with the double conversion application, because we're completely decoupling the source from the load, we're eliminating those transients, right? But it certainly doesn't mean that everything's just going to be perfect, right? And a lot of the harmonic content or concern is literally from the inverter itself, right? Because you're right, we're, how many times a millisecond we're chopping these little tiny, chunks out of the electrical signal to create that sine wave for the load, right? Well, the load wants this. We're ultimately generating something that looks like that, but on a microscopic scale. How much it does require filtering, right? We need capacitors and reactors and things like that. Over time, we've needed a lot less, and that's had a lot to do with the efficiency and the footprint changes of UPSs. If we looked at UPSs from, the 80s and 90s, we'd had 2-layer inverters, right? And we could only switch basically at the full top and bottom wave cycle, right? So we're all on or all off. And so the capacitor and reactor and filter banks needed to support that to turn this big, giant, blocky mess into a coherent wave cycle was massive, right? We need a ton of components, and those were maintenance intensive, right? We needed to replace AC caps every 7 years roughly, and DC caps about every 5 because we would wear them out, trying to keep a healthy sine wave on the output. Whereas now, much more friendly for those components, much less of them required. The switching technology, and really it's a material science issue, right? In the late 90s into the early 2000s, we just made massive advancements in material science around switching devices. And the thing I always like to point to for that I think is easiest is flat screens. We went from tubes everywhere to flat screens everywhere. And the transition happened in a very short period of time. And the price of flat screens was it's ridiculous how cheap you can get a giant flat screen when a 20-inch computer monitor was $1,500 20 years ago, right? So you'd go broke in one of those for your gaming rig, right? Because you wanted to have one. And before that, even in the nuclear power plant on the ship, I was on the USS Carl Vinson aircraft carrier in the Navy, we had one flat screen on one of the monitoring panels in the entire plant, and it was just all red. So it's monochromatic. It's one color, right? That was it. Navy nuclear power, we always just say we're operating the latest in 50s technology anyway. So, it's like, it's the same kind of thing. So what's the most reliable and what has worked for the last 50 years? Well, we're not changing that kind of a thing. But, we went from, if you saw a flat screen, it was one color, right? It was red or amber or green to, hey, there's more colors. And it all has to do with the material science and the doping and how we created different switching devices and LEDs to ultimately open the door for all that technology. And that just shows up in the UPSs as well, and those switching devices and the speed of our computers and everything else, because ultimately we're using the same type of materials there.
There used to be pretty typically isolation transformers on input and output, right?
Correct. So we used to have what we'd call transformer-based UPSs. So your old 2-level inverter UPSs would actually have input and output transformers to step up and step down the voltage for the switching devices and components internal to the UPS, because they couldn't handle a lot of heat, but they could handle higher voltages. And so in a commoditized industry, believe it or not, it was less expensive to have giant transformers built into the UPS for that cost point to just step up and support the internal components than it was to have more internal components and more switching devices in there. The switching devices themselves were also really suspect. Turn of the century, we used to spend a lot of time poring over mean time between failure documents, where we looking at what's the mean time between failure of your switching devices and your UPS and your SCRs and your transistors and your UPS. Ultimately, that only lasted a few years. We realized that everybody's buying the components from the same place. There's only a few manufacturers in the world to make these big switching devices that we're going to put in UPS anyway, and everybody was buying the same ones. They just configured them differently. And so the difference between application and manufacturers and things like that today is really in the engineering and application of their specific design more than it is a supplied component per se, right? So it's not quite that much difference. So the other piece that I think ties into mean time between failure historically that's become more prevalent now is we've kind of moved on from mean time between failure is mean time to repair. Right? So we've kind of come to the understanding that we have much more reliable components now, and they're more trustworthy, so we're not focused on the individual component, but the reality is they're still man-made. They're going to fail. We're going to lose components of that. And so how fast can we repair something when it does break, right? So before, historically, a UPS failed, or any electronic equipment back then, it was usually soldered in or hardwired into a board that might not be changeable unless we're taking the whole thing down for a long period of time. Technicians have to be in and out of there. It's a week to redo things. There actually might be resoldering connections, right? So there's been a ton of focus on modularity, right? Like, how can I design around components that can be quickly swapped out? 15 years ago it was just about how fast can I get these cards in and out. Now we're at the point, it kind of started, it started before that, but how can I now remove entire sections quickly, right? How can I have entire inverter rectifier sections? I'm removing them. How can I just swap the static switch out in one move, right? How can I change out some of the controls portions of our intelligence modules of the UPS out quickly, Mike? So, and not only quickly while taking the UPS down for maintenance, but then do we have some components we can actually change live while the system is functioning? So I don't even have to go to bypass. I don't have to interrupt the support for the load. The load will still be fully supported by the UPS, and I can swap components out, right? How can I change those components out? Those kind of things. So, there's been a lot of emphasis and focus, and then a lot of supply chain support for that. Like, okay, if we're going to have this modular type application, well, those modular components need to be readily available. Doesn't do me any good if I can change it out quickly on site, but it takes me 6 weeks to get one. I've kind of defeated the purpose, right? So many years ago, you'd see specifications come out from engineers that would say, we need all these spare fuses and all these spare cards, and there were spare parts kits that someone might specify, and there'd be X number of things. We've gone away a lot from that as a whole. We don't see much of that anymore, just because service support organizations for most of the manufacturers are pretty good. There's always some outliers, but if you're well supported locally with a robust field engineer staff, as usually most of the bigger manufacturers are, you're probably covered for parts pretty well, right? So they can have access to those parts, do those repairs in short order. Some of them are designed for you to repair yourself as an end user. Even can go in if you're reasonably skilled at that. You can swap some components out yourself without there being any issue. So definitely some big changes in the industry that way that have been very positive.
Yeah, I mean, not even with UPSs alone. It's kind of just the entire design of a data center and all that. I know with UPSs, we don't specify any spare parts now, but we always do internal redundancy.
Absolutely.
So, we do usually 2 or 3 20 kW modules, typically set up as N+1. So 2 of them are always can share if they needed to, but you always have a spare built in right then and there.
Absolutely.
If one goes down, and it does take 3 weeks to get a new part, you're not totally out of.
Correct. That's even a conversation that I end up having with a lot of end users, where you'll still have an end user mentality where, like, we need 4-hour response, or we have to have all this stuff. And it's like, well, we designed you a 2N data center with redundant modules in those components. Like, it's okay if you lost one because you're still 2N. It's okay if you lost, we can now design with the modular scalability in a way, especially, heaven forbid, we design a data center and the customer doesn't load it to the numbers they told us they were going to, like every time.
What is that?
Right, exactly. So we almost always have some amount of additional availability left inherent to the system. So we don't have to go into panic mode when an alarm goes off that a module has failed or some issue has happened. It's, okay, let's calmly assess the situation. I'm still have this level of operational capability. I might still have some redundancy left, or maybe I'm still 2N, whatever it is. Like, okay, the sky's not falling, but yes, let's get it addressed and repaired. But I find a lot of customers spending so much money on 4-hour response or all these kind of really fast responses when, next business day would be fine. You don't even need somebody to show up on the weekend. So you had a power module go bad on a Saturday. You're still 2N. You still got additional modules there. Like, how far are we really away from a concern from the design standpoint of the space versus how it's actually operating, those kind of things. So because there's just so much money that could be saved. I mean, people are paying so much money for certain levels of response, and a lot of people are trying to push them and sell them. I get it. I'm just not in that court. It just seems like a lot of wasted money for the way some spaces are. There's some that probably should have it and some that require it, but quite a few others aren't needing it. One thing I just wanted to get back to that we talked about earlier was just kind of the batteries in general, and just kind of where lithium's going is you can already see even in some of the high-end cars that the starter battery isn't just a regular lead acid battery anymore. If you go to a higher end car dealership or start looking at some of the cars, you'll actually see that just the regular starter battery in a normal internal combustion gas engine car is a lithium ion battery that's just this big.
Okay.
And it makes sense for automotive manufacturers too. Like, why would I put a 40, 50 pound battery that's this large in the car, and it's hard to fit under the hood, and it's already enough of an engineering thing to find a home place for that much weight in this location, whereas it's like, hey, I can take 30, 40 pounds off the weight of this car, which helps its efficiency as a whole, weight, gas mileage, all that, and it's now this big. I can like put it in the footwell of the driver compartment, or I can stick it in the trunk real easy, or anything else. So you just kind of see traditional locations for valve regulated batteries just being taken away by lithium everywhere, which is kind of why I see it's having such a strong effect on just valve regulated lead acid batteries in so many industries, not just ours. It's hard to see a real good long-term home for those. I mean, we'll see. I mean, I'm sure they're out there looking for some and trying to find a place to keep that going, but that's a massive industry that's in a pretty rough transitional period right now, it seems.
Yeah, I know we always get a lot of questions on. One of our customers, at least, is hesitant to make the switch because it's not a proven technology, at least in their eyes. But really look at it, and it's been around for a long time.
Yeah, the cabinets we're talking about right now, I mean, Samsung owns most of the U.S. market by far. I mean, they put more lithium-ion batteries backing up UPS systems than every other manufacturer combined. Their batteries, they've been manufacturing them for 13 years, something like that. So we're definitely not at the new point, right? You're not doing something new. I mean, even just like I said before, I haven't seen a UPS installation over 200 kW not be lithium ion for probably at least 5 years, maybe longer. So we're definitely not. You're not doing anything new. You're almost a late adopter at this point, right?
A little bit, yeah.
So it's really fully baked in those applications. You're hard pressed to find a better application for that at this point. So, and that's just the way. I mean, lithium is just kind of growing and showing up everywhere. Questions about the manufacturing and the mining and everything else. There's no doubt about that. At some point we'll probably end up mining our own landfills. Right, we're going to go back. Who knows? We've thrown away things for hundreds of years that we probably now are like, we could really use that. Yeah. But once the price hits the right point, then we'll go back and dig into those yet. Yeah. I think we're quite a ways away from that yet, but who knows? That definitely could be a thing that could happen.
I've never thought about that before, but that's definitely.
Yeah, just think about some of these massive landfills that we've made over hundreds of years that we put everything in them until. When did we really start recycling? Right. 30, 40 years ago, maybe? Yeah. There's a lot of material there.
There is.